All right, here's part 3. We're going to do, what are we doing here? One more example, and then we will be done with this section. So in this example, we've got capital F of S is equal to 2s squared plus 10s over s cubed minus s squared plus 3s plus 5. And we're looking for the inverse Laplace transform. All right. Again, partial fractions. Is it proper? Yes, it is. So we can get started right away. S cubed minus s squared plus 3s plus 5. We look for a root. Minus 1. Yeah. S equals minus 1 is a root. Because then we have minus 1, so there's minus 2, minus 3, so there's minus 5, plus 5. All right, so that means that s plus 1 is a factor. Work out what the other factor is, and you'll get s squared minus 2s plus 5. Oops. All right, now we want to factor that second one. But if you work out what the roots are of that, you would get 2 plus or minus the square root of 4 minus 20 over 2. Now for us, when we're doing roots of a characteristic equation, for example, that's okay. We deal with complex roots. We work with them, we accept them. But when you're doing proper fractions, you do not. So when you're doing proper fractions, proper partial fractions, when you're doing partial fractions and you see that you have complex roots, you do not factor it into complex factors. You simply say, okay, well, then I've got no real roots, so that means that this thing is an irreducible quadratic. And then you leave it like that. All right, so if I've got an irreducible quadratic, then I stop factoring it, and I take my original equation, my f of s, my original function, f of s. I've got 2s squared plus 10s on the top, and on the bottom I've got that factored expression, s plus 1 times s squared minus 2s plus 5. And I need to write down the form of the partial fractions decomposition. All right, so s plus 1 is a linear factor. It's not repeated, so I just get a over s plus 1 for that factor. The second one is an irreducible quadratic. It's not repeated, so I just have one fraction with it, and it's got this as the denominator. But the numerator has the form bs plus c. Okay, multiplying both sides by that denominator, I get 2s squared plus 10s is equal to a times s squared minus 2s plus 5 plus bs plus c times s plus 1. Okay, let's do this one in the traditional way. Multiply out the entire right-hand side, collect like terms, and compare coefficients. Okay, so on the right, then, I get as squared minus 2as plus 5a. Then I multiply that other part out. What do I have? bs squared plus bs plus cs. So I have b plus c times s plus c times 1. Collect like terms, and I have a plus b s squared. Then collect the a terms, and I have negative 2a plus b plus c times s. Collect the s terms, and that's what we get. And then collect the constant terms. So the constant is 5a plus c. And now equate coefficients. So equating the coefficient of s squared, I get the equation a plus b equals 2. Equating the coefficient of s, I get negative 2a plus b plus c is equal to 10. And equating the constant, we get 5a plus c is equal to 0. And now we have to solve those for a, b, and c. All right, well, so I can start with the third one. And this will give me c equals negative 5a. I can substitute that into the second one to get negative 2a plus b minus 5a is equal to 10, or negative 7a plus b is equal to 10. All right. What do I want to do then? I don't know what I was doing in my notes. Well, we can combine that with the first equation, right? And if I take that first equation and multiply it by, well, what can we do? We can take the first equation and subtract the second, right? So I can take my a plus b, and so what can we say? A plus b minus negative 7a plus b is equal to 2 minus 10. So that gives me 8a is equal to negative 8. So a is negative 1. And then from the first equation, b is equal to 2 minus a, so b is equal to 3. And then from the equation that's at the top of the screen right now, c is negative 5a, so c is 5. And so putting that all together, I've got f of s is negative 1 over s plus 1 plus 3s plus 5 over s squared minus 2s plus 5. And I want the inverse Laplace transform. So the first one, you can read it right off of the table. But for the second one, I'm going to need to use the tricks from one of our earlier examples. I need to complete the square in the bottom, and then I'm going to need to do some algebra manipulations on the top. So let's look at that part separately. So I have 3s plus 5 over s squared minus 2s plus 5. Let's complete the square on the bottom first. So I get s minus 1 squared. It's s squared minus 2s plus 1. I need to add another 2. So plus 2 squared, plus 4. Writing 4 is 2 squared. And I know I need to work s minus 1 into the top. So let's take that s and write it as s minus 1 plus 1. And then I've got a plus 5. Okay. So on the top, I get 3 times s minus 1. Plus 3 plus 5, so plus 8. And on the bottom, I've got this thing. All right, so putting that back into my capital F, we get capital F of s equals negative 1 over s plus 1 plus 3 times s minus 1 over s minus 1 squared plus 2 squared plus 8 over that denominator. But now if I'm going to be reading that off of the table, my numerator can't be 8. It's got to be a 2 because I've got the 2 squared in the denominator. So instead of 8, let me write it as 4 times 2 over s minus 1 squared, plus 2 squared. All right, so I've now manipulated my capital F so that I can read all of those inverse Laplace transforms off of the table. So now let's do that and we will be done. So inverse Laplace of f is now negative e to the negative t plus 3 e to the t, because of that s minus 1, cosine bt, b here is 2, so cosine of 2t, plus 4 e to the t sine of bt. There we go. All right. We can make that a short part, and that way we can start section 7.5 with a new video. So we will see you in part 4.